Professor Blunt, we'll just start with a very basic question, and this was a question that I personally had. That usually gases do tend to have a certain form of viscous fingering, and they lead to premature breakthrough, and that reduces the flow mobilization potential and also little lower capacity of storage in the subsurface. And we currently have two gases that are being considered heavily for subsurface flow, like CO2 and hydrogen.
Yeah.
So which of these two gases experimentally or from your insights is like a major concern to shows a much detrimental effect of viscous fingering?
Okay, excellent question. So yeah, I've sort of considered what happens at the small scale, sort of this scale. But when we look at the larger scale, particularly as subsurface formations are very heterogeneous, then you do get this viscous fingering phenomenon. The reason is that CO2 and hydrogen are much less viscous than water, and also they're more buoyant. So there's a tendency to create this viscous instability and then to channel along high permeability regions and to rise upwards. Now, depends on the application. In CO2 storage, funnily enough, this isn't a great concern. The CO2 plume essentially can then get dispersed over a wide volume, and then it's at low saturation and can easily be trapped or dissolve. The concern, however, is that you know how it's going to spread, and you can ensure that they won't then spread so that it escapes up through a fracture or a fault or even an abandoned well. So that's one of the things when it comes to design and particularly licensing that's a concern. For hydrogen storage, actually, the way you view it geologically is really very different, because there you don't want the hydrogen to disperse everywhere. You want it to be trapped. So if you can see my board, actually what you want is you want some low permeability region here, and you want to inject the hydrogen so that it actually fills a known trap. So there may be viscous fingering, but in the end, you just want the hydrogen to accumulate under a trap. So it's a little bit different in terms of how you're viewing the geology. So for hydrogen storage, you're normally looking at a location where it's really going to be high saturation under here. CO2 storage, you can do it this way, and in fact, that's where most people start, but actually you build up a lot of pressure often. So CO2 storage is a little bit different. So I don't necessarily view it as a problem, but it is something that needs to be taken into account in process design.
Thank you, Professor. That was wonderfully explained, and it really made a lot of sense to me also. So, Professor Knight, we have a question now that you are one of the foremost experts working in, subsurface flow media imaging, and a couple of our audience, they are working in gas hydrate formation. So they had a question like, can we identify CO2 hydrate formation steps using CT imaging? Like how the hydrate crystallizes and then again it grows. Would it be possible to do through CT imaging? And what are some of the traces that can be used in this process?
Okay, so I'm not an expert in gas hydrates, so I've got to be a little bit careful what I say. In principle, I think this technology could be used. Okay, the two things you need to consider is first is resolution. While there's a lot of flexibility with X-rays, generally speaking, we're looking at systems down to a resolution 1 micron. And the second is, as being pointed out, is phase contrast. So in our experiments, in order to get a good contrast between the phases, we what's called dope the brine. So the brine is normally, the water has an iodine salt in it. Now that's okay for our applications, but becomes more challenging in others where that's going to affect the phase behavior. So I'm not sufficiently expert to say yes it will work or no it won't, but those are the things you certainly need to think about, and you do need to find some way of distinguishing between the phases. So it's normally with a salt, but that may mess up, obviously, as I said, mess up all the phase behavior.
Thank you, Professor. That was helpful. We have another question that's coming up regarding the wettability, and an audience member has just put up this question that how important is wettability for oil and gas recovery processes?
Oh, absolutely vital. I mean, that was what I tried to demonstrate with that one example. So it's well known if it's a water wet reservoir, you get a lot of trapping of oil, but actually a fairly efficient displacement. So up until breakthrough, you get maximum recovery. So at a field scale, actually water wet seems good. Oil wet is terrible because in fact, the oil basically just retained in the pore space and doesn't get produced. But what we're suggesting here is actually the sweet spot is this mixed wet. Now, it's something difficult to design. You can try and modify the wettability using low salinity water flooding or surfactant injection. So this is what's suggesting is what is the sweet spot. It's not actually strongly water wet behavior, but something that's more mixed wet. So yeah, it has a big difference to recovery.
And Professor, since we are on the topic of wettability and when we perform CO2 injection into the subsurface, CO2 also tends to adsorb on the reservoir rocks and or like adhere to the reservoir rocks, and that may have like a different type of effect on the rock wettability. Is it an important concern by determining, what is the CO2 storage capacity of a reservoir over a long period of time?
Yeah,
Like
I mean, it has an effect. Let's go through it in terms of timescale. The principal effect when you inject CO2 is, in fact, you're just adding mass or adding volume. So the first thing to monitor and control is pressure buildup because you don't want to induce seismicity. You don't want to create any fracturing. The second thing that happens is obviously the CO2 is moving. So it's the migration and the viscous fingering that we talked about. The third thing is then as the CO2 migrates, it will get trapped by this capillary trapping mechanism that I've talked about. Then there'll be dissolution into brine. There also may be reaction. It is thought that at the field scale, the amount of reaction is relatively small because the system quickly gets buffered, but is a concern in the near wellbore area. So you can get a number of things. You can get salt precipitation, you could get dissolution of carbonate material, and that could, say, change the strength of the rock. So these are all considerations, and they are all things that people do look at. Most of the storage sites, though, that people are considering, certainly in a UK context, are sandstones, where the amount of chemical reaction is relatively modest.
So since we are on this topic of gas storage, and there are a couple of questions around that. We tend to perform CO2 storage also. We tend to store hydrogen for a much smaller scale, CO2 for a longer scale. So what are some of the considerations to have when we are storing CO2 in like a depleted oil and gas reservoir, storing CO2 and hydrogen in a depleted oil and gas reservoir, or storing CO2 or hydrogen in a saline aquifer?
Okay,
some of the important considerations to have.
Yeah, so they are different, right? Because the CO2 you want to put underground, you don't want it back out.
Yeah.
So there, with CO2, you're not worried about the dispersal of the plume, and you've got to be concerned in a depleted oil field, but with the completions of the wells. So when you abandon the wells, you need to make sure that it's CO2 resistant cement. That's normally the major concern, actually. In a saline aquifer, the major concern is overpressurizing the formation so that you induce fracturing, but you're not worried about the dispersion of the plume, right? Because that's actually helping long-term storage. With hydrogen, it's the other way around. With hydrogen depleted oil field, the major concern actually is biological bacterial activity, that the bacteria actually eat the hydrogen together with the hydrocarbon and create methane. So you are not producing hydrogen anymore, you're producing methane. Now, on an energy perspective, it's not catastrophic, but from a CO2 perspective, it's not very good. Because now you've got a hydrogen methane mixture, and if you burn that, you're producing CO2. So most people are thinking that you'd either be in a depleted gas field or a depleted or a saline aquifer, where it's essentially a more or less inert environment. And there the concern is you need to maintain the hydrogen at a high saturation because you want to get it back out, right? So you don't want to sort of spread it out.
So this was exactly my next question, that what were some of the important considerations to have during subsurface hydrogen storage, but you already got to that. I have another question, that how does the porous structure of gas diffusion layers, impact their performance?
Oh yeah, so that's an excellent point. So the gas diffusion layers need some of this plastic binder, right? Because that's the wettability. But in terms of pore structure, you still want to have a very high porosity. So what we found is you want to have a relatively small amount of binder so that you maintain a porosity of around 60, if not 70%, because that's best for flow. If you put in too much binder, so it becomes more hydrophobic, what you do is you filled up the pore spaces. So the idea is to manage to keep a relatively loose fibrous structure is ideal.
Okay. And there's another question that what is the relation between pore sizes and the storage energy density of any porous material, let's say for hydrogels or aerogels?
So energy, that's it depends exactly how you mean it. In terms of just pore structure, if it's just the capacity is mainly determined by the porosity. By having smaller pore spaces, essentially it's less permeable medium, so it's more difficult to inject and withdraw. Okay, I mean, if you're doing other things, if you're looking at absorption phenomena and other things, clearly it's related to surface area, right, which will obviously be larger with a smaller pore structure.
Okay. So, Professor, a couple of questions, and then we'll be closing the session. And one of the questions that we have is that since a lot of our attendees, they are early stage faculty members and researchers, they would just like to know that what are some of the emerging areas of research in which they could try to look at and then again do some research to get some published papers. So if you would like to share something, provide some words of wisdom or some direction to them, that would really be nice.
Yeah, I think the major thing here is to look at flow and porous media as a scientific discipline, not just as something you tack onto an application, and particularly to look at it in terms of the design of materials. So one of the newer things we've spoken about here, the gas diffusion layers, packed bed reactors, these types of application, and how you design the pore structure, and sometimes the wettability or the inert versus reactive components, till you get optimal process design. And the advantage here is we've got modeling tools that can do this, pore scale modeling tools that are very efficient, but we also have new experimental techniques, of which obviously the micro CT imaging is one. So my view here is to think about flow and porous media as a way of designing better processes. I think that's where the biggest impact is going to be. The second thing I would say to junior researchers, and it's a difficult thing to say because I know many of you, you want to get another paper out, you're worried about how to, get a postdoc. But probably what you want to do sometime is to sit back and think, what are the important problems? What are the big problems, both in terms of application, dealing with climate change, providing enough water, right? So think about the big applications, but also think about the scientific problems associated with this, and to make sure that you're working on those. Because when you think in 20 years' time, the people who are best established are often not necessarily the people who are smartest. Often they've been fortunate, it's true, but often it's because they tackled the big problem, right? They didn't write 100 papers on something that actually turned out to be a bit niche. So that would be my advice, right? Be ambitious. Think about the things that in 20 years' time are really going to make a difference, and make sure that you're associated with that type of activity.
Thank you. That's a wonderful thought. And since, can we take one more question?
Yeah, sure.
Okay. So, Professor, we were on this topic of micro CT. So a question has come up that an attendee is trying to create a wormhole inside a carbonate core for some of their client work that is using HCl and another retarded HCl. They just want to identify that if a wormhole formation takes place, can they do some permeability modification studies using CT imaging?
Yes, absolutely. Right. There are two ways, and we've done this ourselves in our own labs. So you can take images while the wormhole is developing, so you can see the wormhole develop. And there are two ways in which you can measure the permeability change. One is actually numerically. So you've got an image and then you solve the flow, basically the Navier-Stokes equation, or in fact, actually just the Stokes equation through that image to predict the change in permeability. The other, which we do now, is as you're flowing the fluid, you monitor the differential pressure. So you actually get basically a continuous measurement of permeability. So yeah, absolutely. This is a very nice application to look at reactive transport. And we've looked at this in rocks. We're now beginning to look at this in cement, obviously to design how you should abandon wells, for instance. So no, it's a very nice application of this technology.
Thank you, Professor Blunt. Aparna, over to you.
So this brings us to the end of today's ACS Science Talk. We hope that you enjoyed this broadcast, and we invite you to view the edited recordings from the past events in the ACS Science Talk library. At the end of session, you will receive a brief survey. Kindly share your feedback with us so that we can continue to improve and serve you better. On behalf of all of us at ACS, thank you for joining us today. We hope to see you again for more ACS events. Until then, stay safe and stay healthy. And thank you so much, Professor Blunt, for joining us.
Been a pleasure. Thank you.
Bye, Professor Blunt. Bye, everyone.